This is part 2 of section 5.2, properties of rational exponents and radicals. This video is going to talk more about the more complex, and I put complex in quotations because we will actually deal with complex fractions when we get to chapter 7. But for now, we'll think of these as complex because they are more complex than the ones we dealt with in section, or the first video of section 5.2. So when we're talking about complex radical expressions, what I'm thinking about is something along the lines of, let's say 2 over 4 minus the square root of 7. How can we simplify that? That would be an example of a complex radical expression. Something where you've got a difference in the bottom, could be a sum, you got a square root, you might have a square root on top as well. I mean, we could easily make this the square root of 2, and that would be also a complex radical expression. The question becomes, how do we deal with that? Okay, so that's what this note this little note right here says. If the denominator has a sum or difference involving a radical, and that would be what this is. Okay, what we're going to do is we're going to multiply the top and the bottom, and maybe of the fraction, you might want to put right there, the top and the bottom of the fraction by the conjugate of the denominator. And the question then becomes, what's a conjugate? Well, conjugate here, I've got a definition for you. It's a binomial form by switching the sign of the second term. So really, if I gave you 4 minus the square root of 7, the conjugate of that would be 4 plus the square root of 7. Or if I gave you something like the square root of 6 plus the square root of 11, the conjugate of that would be the square root of 6 minus the square root of 11. That's all a conjugate is. It's a binomial, two terms, bi meaning two, and all we do is switch the sign in between them. Okay, so we go from 4 minus to 4 plus, or square root of 6 plus to the square root of 6 minus, and that's really all there is to it. Now, when we simplify these expressions, it might get a little hairy, might be the right word. It's going to take a little bit of time. It's not going to be something that's super quick, but it's not something that is super difficult either. So let's take a look at this first example, 1 over 5 plus the square root of 3. So what the direction says, or what the note says to do, is to take the top and the bottom of the fraction, multiply it by the conjugate of the denominator. So the first thing we need to do is we need to multiply this fraction by another fraction. It's the conjugate of the denominator. So 5 plus the square root of 3, the conjugate of that would be 5 minus the square root of 3. And we're going to do it on both sides of this fraction. Okay, we're multiplying this original fraction by 1. We're not changing its value, we're simply changing its appearance. Okay? On the numerator, what we're going to do is we're going to distribute. We're going to take 1 times 5 and 1 times negative 3, because we're taking this numerator times this numerator, which is going to be pretty simple. It's going to be 1 times 5 is 5, and 1 times negative square root of 3 is negative square root of 3. Pretty straightforward. The bottom, what we're going to do is we are going to FOIL. Hopefully you remember the FOIL method. First, outers, inners, last. So the first term would be 5 times 5, so that's 25. The outside terms would be 5 times the negative square root of 3. So positive 5, negative square root of 3 becomes negative 5 times the square root of 3. We really don't know what that's going to be. Then we go to our inside terms. Positive square root of 3 times positive 5 is positive 5 square root of 3. And then lastly, we have the last. And positive square root of 3 times negative square root of 3. Positive times negative is a negative. Square root of 3 times the square root of 3 is the square root of 9. And then we'll try to clean this up. What I hope you notice is that these middle two terms right here, this negative 5 square root of 3 and positive 5 square root of 3, they are opposites. They just simply go away. They cancel each other out. Why we want that to happen is because now what's going to happen, remember when we're talking about simplest form, we don't want radicals in the bottom. Well, the 9 is a perfect square, so that is going to go away. This is going to become just 3 minus 3. And the denominator works out really, really well. All we're left with is 25 minus 3. And that, I'm pretty sure I can do that in my head. That's 22. Okay? So now when we talk about simplest form, we don't have any radicals in the bottom. We're not going to have any fractions underneath a radical. All we need to do, there's nothing we can really do to clean this up. 5 minus the square root of 3 that's about as simplified as we're going to get. It's going to stay 5 minus the square root of 3. And that right there is your answer. Okay, sometimes it works out really, really well. Sometimes it takes maybe a step or two more, but that's all there is to it. Multiply the original fraction by the conjugate of the denominator. Multiply it out. Sometimes you might have to FOIL both the top and the bottom. Sometimes it's just the bottom. Well, every time it's just going to be the bottom. But what I want you to notice, or what I hope you're going to notice, is that as we keep doing this, the reason we multiply by the conjugate is because when we FOIL, these middle two terms are going to cancel out every time. You really don't need to do the whole FOIL method every time. Really, you can just do the first term times the first term, last term times the last term, and you're going to get your answer, because these middle two terms, when you do the FOIL method, are going to cancel out every time. You don't need to do that middle two terms. You don't need to do the outers and the inners. You can just do the first and the last, and you're going to get the same answer. Save yourself a little bit of work. Let's try another one here. Square root of 7 over square root of 10 minus the square root of 2. Once again, we have square roots in the bottom. We don't want that to happen. So we're going to take this times the conjugate of the bottom, which is the square root of 10 plus the square root of 2. Just switch the sign in between them. Square root of 10 plus the square root of 2. And let's multiply this out. Okay, so I'm back to orange. Actually, I'm going to do this in purple first. We're going to, purple there, we're going to distribute the top. Square root of 7 times the square root of 10 becomes the square root of 70. That's the product power coming into play here. And we'll do the same thing. Square root of 7 times the square root of 2 becomes the square root of 14. Okay, and then do it over the bottom. Again, this is one of those things where the middle two terms, the inners and the outers, are going to cancel each other out. So really, we just need to do the first times the first, the last times the last, and see what comes out. Okay, so square root of 10, go back to purple, square root of 10 times the square root of 10 gives me the square root of 100. Square root of 2 times square root of 2 is the square root of 4. And this was positive times positive, so that's going to be a positive. This is negative times positive, so that is going to be a negative. Okay, so let's clean up what we can. Do we know the square root of 70? The answer to that is no. Is it a perfect square? No. Is it divisible by a perfect square? Well, the perfect squares would be 4, 9, 16, 25, 36, and we're too big now after that. So 70 is as far as it's going to go. That's a number that's going to stay there. Same thing happens with 14. 14 is not a perfect square. Well, yeah, it's divisible by 7, but 7 is not a perfect square either. And same thing with 2. So 14 is about as far as we can go with that as well. Our numerator is done here. Square root of 70 plus the square root of 14. That's what we're going to leave it as. The denominator, though, that can change. The square root of 100, hopefully you remember or realize that that's 10. Square root of 4, that's 2. And again, once you take the square root, this has not become the square root of 2. This is just 2. The square root of 4 is 2. It's not the square root of 2. Okay, so then we'll have just 10 minus 2. So our final answer here for number 2 is going to be the square root of 70 plus the square root of 14 all over 10 minus 2, which is 8. And that right there is your final answer for number 2. The next big topic in section 5.2 is the idea of like radicals. Now, like radicals are radicals with the same root and the same radicand. And radicand is a fancy way of saying the stuff under the radical. Okay, so like radicals, I got one example here, 4th root of 10, 4th root of 10, they are like radicals. You can kind of think of them as like terms. Think of them as variables. Think of this as x plus 7x. Okay, if you had something like that, if you had x plus 7x. Well, this would be pretty straightforward. That becomes 8x. 1x plus 7x gives you 8x. We can treat these radicals just the same way. If I have 1 4th root of 10 and I add 7 more 4th roots of 10, what I'm going to get is 8 4th roots of 10, and that's your answer right there. When you're asked to simplify, we're just combining like terms. Okay, these are like terms. Think of them as variables. 4th root of 10, 4th root of 10, x, 1x plus 7x is 8x. So 1 4th root of 10 plus 7 4th root of 10 is 8 4th root of 10. If you get something like this where it's written as a fraction, remember, the 1/5 power is the same thing as the 5th root. So you could rewrite this or think of this as 2 times the 5th root of 8 plus 10 times the 5th root of 8. Once again, your radical parts are exactly the same. They are like radicals. So what we can do is all we need to do is take this 2, add the 10, and put the 5th root of 8 on the end of it. So we've got 2 plus 10 is 12, so we can say that's a really bad 12. Let's try that again. 12 times the 5th root of 8, and that's all there is to it. That's your answer for number 2. Now, sometimes you're going to get an example where the radicals are not the same. The numbers aren't the same, okay? And that's a key. The numbers have to be the same. Just like here, they're both 10. Here, they're both 8. In this case, they're not the same. But what we can do is we can kind of manipulate this to make it the same. 54 is not a perfect cube, but it is divisible by one of the perfect cubes. If you look at that half sheet I gave you, one of the perfect cubes that 54 is divisible by, or the only perfect cube that 54 is divisible by, is 27. Okay, so what we can do is we're actually going to rewrite this. We're going to simplify this. Cube root of 27 times 2 minus cube root of 2. So the only thing I've changed here is I've changed 54. Everything else has stayed the same. The cube root of 27, Let's see, cube root of 27, that's 3. So we're going to have 3, and we're left with the cube root of 2. We don't know what the cube root of 2 is, minus the cube root of 2. Now, what I see a lot of people do when they first do these types of problems is they think of these, well, the cube root of 2 minus the cube root of 2 goes away. They're just left with 3. And that's not correct. Okay, think of them as variables. If I have 3 x's and I take away 1, that means I have 2 x's left, and it's 2 x's. So what my answer here is actually going to be is 2 cube root of 2, and that's your final answer. 2 times the cube root of 2, because you had 3, you took away 1, you're left with 2 cube roots of 2. Again, think of them as variables. Okay, like radicals are just like they act and behave just like terms. Okay, if we were thinking variables with the x's that we had up in here. Okay, last one here, number 4. Cube root of 5 plus the cube root of 40. Again, the numbers are not the same, so right now they are not like radicals, but what we can do is we can manipulate one of these, or both of them if we had to. In this case, it's going to be 40. So we're going to leave this as the cube root of 5. 40 is divisible by one of the perfect cubes. The perfect cube that it's divisible by is 8, so we'll make this 8 times 5, and that's convenient because we're going to end up having 5 underneath the cube root. The cube root of 8, so let's see, this still says cube root of 5. The cube root of 8 is 2, and I do not know the cube root of 5, so that stays the cube root of 5. And once again, I have 1 cube root of 5 plus 2 cube roots of 5 leaves me with 3 cube roots of 5, and this is your answer there for number 4. All right, the final thing in section 5.2 is the idea of when variables are underneath a radical. So when variables are underneath a radical, you need groups of n, and n is, I'm going to underline this, and I'm going to circle that because those are the same. When I reference n, groups of n to be able to take any variables out from under the radical. So you need groups of, in this case, in number 1 here, you need groups of 5, okay, to take any variables out from the radical. So I'm going to show you how to do the first one here. So we have the 5th root of a to the 12th. Now we need groups of 5. So how many groups of 5 can I take out of 12? Because I have 12 a's. This says a to the 12th, so that means 12 a's. When you take 12, if we're taking groups of 5, that means we can take 2 groups of 5. So what we're going to have then is a to the 2nd power. And how many were left over? Well, if I take 2 groups of 5, that's 10. That leaves me with 2 remaining. So I'm going to have a to the 2nd, and I'm going to do this in a different color, times the cube root, not cube root, 5th root, since it was the 5th root originally, of a to the 2nd power. Okay, so that's your answer there for number 1. Just maybe a couple of notes. This is the number, the exponent on the outside, the number of groups that you can take out. Sorry for the handwriting there. So the exponent there is the number of groups that you can take out, and then the exponent on the inside is how many left, or how many remain after your groups. Okay, so how many remain? That's your other exponent. Everything else really stays the same. It's still going to be the 5th power, or the 5th root, because it was the 5th root here. It's still going to be a, because that's really not going to change anything. Really, we need to know how many groups can come out and how many are left underneath. Okay, so now for number 2, we've got multiple variables. We got a number. Think of them kind of individually. So let's start with 4 here. So the 5th root of 4. 4 is not a perfect 5th power. It's not divisible by any perfect 5th power. So what we're going to do is we're actually just going to leave it right where it is. It's going to stay underneath the radical. So we're still going to have 5, 5th root, the 4 stays. We can't do anything with it, so it stays underneath. Now let's move on to the a's. So I did the 4 in red. We'll do the a's in blue. I've got 8 a's. I need groups of 5. Okay, so how many groups of 5 can I take out of 8? That would be 1. So we will put 1a out front, so a to the 1st, and really you don't need the 1st power because that's kind of implied, so we'll erase that. We took 1 group of 5 out of our a to the 8th, which means there are going to be 3 left over. So underneath the radical, we're going to put a to the 3rd power. Okay, now let's move on to the b's. We're looking for groups of 5 out of 14. Again, there's going to be 2 out of there because that could give us 10. So we'll have b squared. And if I take 2 groups of 5, again, that's 10, so we're going to have 4 left over. So we're going to have b to the 4th power left underneath. Lastly, we got to tackle the c's. So c to the 5th, we're looking for groups of 5. We have 5, which means we can take 1 group out. So we'll take c to the 1st, or just c, and we don't have anything left underneath. So if there's nothing left underneath, you don't need to write anything underneath. This is your final answer right here for number 2. ab squared times c times the 5th root of 4a cubed b to the 4th. Kind of a mouthful, but really just take it piece by piece, and it'll go all right. Okay, so number 3. x over the cube root of y to the 8th. Now, this is one we got to kind of think ahead. So we know we need groups of 3 for the bottom, and I've got 8, which is not divisible by 3. It doesn't give us a whole group of numbers, or it leaves us with some underneath. So what I would recommend doing, if you have a situation like that, let's multiply by something so that we can get a whole group of 3 or an even number of groups of 3 to come out of this. And we only need one more because we have 8, so we need one more. So let's multiply this by the cube root of y, or y to the first. Okay, it's the same thing. And we'll multiply by the cube root of y up top as well. Again, we're multiplying by 1, not changing the value, just changing the appearance of the fraction. So in the numerator, what we're going to be left with, let me go back to the pen here, is x times the cube root of y over, now in the bottom we have cube roots times cubes roots, so we can just multiply these. Y to the 8th times y to the 1st gives us the cube root of y to the 9th. Now that works out really well because the cube root of y to the 9th, that's going to work out evenly. We're looking for groups of 3. We have 9, which means we're going to be left with 3 groups, or y to the 3rd outside, and there's nothing left on the inside. So we're not going to have that radical in the bottom when we're talking about simplest form. So the only thing we need to do then is to write the numerator up again, which is going to be x times the cube root of y. And there is our final answer there for number 3. Now for number 4, we've got 14xy over 2x to the 3/4 z to the negative 6. I do have 3 different variables here. When you have something like this, and I can't scroll this screen any farther, I'm at the bottom of this slide, so you're just going to have to kind of bear with me. So what we're going to do here is we're going to split this into separate parts. Okay, we're going to have the 14 over 2, we're going to have the x over x to the 3/4, and then y over z to the negative 6th. Really nothing we can do with that, but we can do stuff or do things with the rest of it. 14 over 2, that's going to be 7 over 1, or just 7. X over x to the 3/4. Remember, this is like x to the first power. So if we have 1 minus 3/4, if I have one whole pizza and somebody eats 3/4 of it, that leaves me with 1/4 of that pizza. So I'm going to have x to the 1/4 power. Okay, I don't have anything to match with the y, so I just have to leave it as is. Y to the first power, or just y. And then lastly is I got to deal with that z to the negative 6. Now ideally we don't want negative exponents, so we need to make this positive. We're going to do that by flipping which side of the fraction it is on. If it's on the bottom and it's negative, to make it positive, we're going to take it up to the top. We're going to have z to the positive 6th. And that's really all there is to it. There's no other, we don't have any radicals, we don't have any fractions, we don't have any like radicals. This right here is our final answer, 7x to the 1/4 yz to the 6th.